So today we're talking about lesson 2-2, which is on graphing translations. For your essential question, I want you to answer, what are we able to identify in vertex form that helps us to graph the function? Now, before we get into the vocab for today's lesson, I want to take a look at the last equation that you graphed in the 2-1 practice. So in the 2-1 practice, you were given an equation and asked to plug your values in from a table of values to find the output or the y values so that you could graph your points to graph your function. So for the last question, number 3, in 2-1, we had y equals x minus 2 squared minus 5. And when you plug these x values in to this equation, you should have gotten these y values here. So let's take a look at how this looks on the graph. So -1, +4, 0, -1, 1, -4, 2, -5, 3, -4, 4, -1, and 5, +4. So this is how your graph should have looked for number 3 in the 2-1 practice. Let me, of course, draw my axis of symmetry here. And this is x equals 2. Sorry about that. So then one of the questions I asked you was to tell me how this differs from the parent function. Now remember, our parent function has a vertex at 0, 0. And we discovered that there is kind of a graphing pattern from the vertex that gives us the next point, which are our perfect squares. So up 1 over 1, from the vertex up 4 and over 2. And then from the vertex up 9 and over 3. So this was the parent function that we found in our 2-1 notes. So how does this blue graph, the graph y equals x minus 2 squared minus 5, differ from the parent function? Well, our vertex is here at 2, -5. Let me actually do that in a different color. I don't want you to get that confused with the pink graph. So our vertex is at 2, -5. So this graph is translated or shifted to the right 2 and down 5. Well, where did that come from? Well, I know we did the table of values over here, but if you take a look at the equation, notice that we have a 2, well, a -2, and a -5 in the equation as well. And that just happens to be our vertex. This is very similar to point slope form that we talked about in our review unit. So let me take a minute and let's take a look at point slope form and see how this is similar to what we have here. So y minus y1 is equal to m times x minus x1. So in point slope form, the x1 and the y1 are what give us our starting point, and from there we would use our slope. Well, notice that here our y is by itself. So what if we move this y over to the right-hand side? If we add the y1 to both sides, we would get y equals m times x minus x1 plus y1. So in this case here, with that negative, because remember in point slope form, we always had to use the opposite sign because that negative was within the equation, we are now only looking to change the sign of the variable that's in the parentheses. And that's the exact same thing that happened with this equation here. We change the sign on this 2 that's inside the parentheses, and we instead go in the positive direction. And then this value here brings us in the negative direction. So this here gives us the vertex of our function. Well, what about the graphing pattern? Did this function here follow the same graphing pattern as the parent function? So from the vertex, if I go to the next point, I'm going up 1 and over 1, so that was a plus 1. To the next point from the vertex would be up 1, 2, 3, 4 over 2, so that's plus 4. And then the next point is up 1, 2, 3, 4, 5, 6, 7, 8, 9, and over 3, so that's a plus 9. So the 1, 4, 9 is the graphing pattern that we use to find the next few points after the vertex. Well, these are our perfect square numbers. So what would come next? 16, 25, etc. Now, I always want you to use as many points as you can to fit on a 10 by 10 graph. So anytime I give you a graph like this on a test, I want you to put as many points as you can on a 10 by 10. So if you're using the graphs that I've provided you with and you're printing them out, you're just going to put as many points as you can on the 10 by 10. If you have your own graph paper, stick to the 10 by 10. You don't need to go beyond that. Now, what's different about this equation from the point-slope form? Because remember, in point-slope form, that gives us a line. So here, notice that we have this square. And that square is what causes our graph to make this parabolic shape. And that square is what gives us a quadratic function. So anytime you have an equation where your highest degree term is x to the second power, quadratic, that is a quadratic function. And again, that is what's going to give us that parabola when we graph. All right, so that is the equation that we saw, again, in the 2-1 that I wanted us to kind of warm us up to what we're going to see today. So let's take a look at our vocab. Our first vocabulary term is vertex form. And this is what that equation was in that we just looked at on the graph. Y is equal to A times x minus h squared plus k. Now the h and the k are what give us the vertex. H is what causes our graph to shift or translate to the left or to the right. So that's our horizontal shift. And the k is what causes our graph to shift up or down. So that is our vertical shift. So h is our horizontal shift and k is our vertical shift. But keep in mind that because this is subtracting the h, that is telling us to use the opposite of h. So hk is the vertex of the parabola, hence the reason we refer to this as vertex form. Now notice we also have this other variable that's hanging out in front of our equation. And the a value, for now, we're strictly looking to see if a is positive or negative. And if a is a positive value, that's going to cause our graph to open upwards. But if a is negative, that's going to cause our graph to reflect across the x-axis. And that's going to cause our parabola to open in the downward direction.